Okay, here we go. I think I've got it framed pretty well, and here's our presenter. Okay, you're ready to go.
Hey everybody, I'm gonna present my master's project, which is development of an autonomous inventory robot for forest nursery management. But first, a biography of myself. I came here to US 1.5 years ago from a small desert town in central Iran. Those are my brothers, that's my family. Since I came, I've only been able to talk to them over video chat. This is our lab.
Just one mildly humorous comment on your previous slide. You see where it says where you say I love deserts.
Oh, I forgot to keep it. It's capitalized with L. I had to.
No. What I was? Do you all know what I was about to say? All right. If you add one S, so it's funny in English, right? If you put one more S in that word, it's desserts, like sweets after the meal, right? So you could say I love deserts and desserts. Yeah.
Or I can put a parenthesis with an extra S.
Yeah. There you go. Yeah. Sorry, I didn't mean that. That doesn't count against your time.
And this is our lab. We try to do like engineering integrated with agriculture and good high-tech. So this is the content of my presentation today. I'm going to talk about background. Some of it are obvious to this class, so I'm going to skip over them. But we'll also talk about navigation, the robotic software and how I developed it, how I implemented it in the simulation environment, and then how we carry that over to experiments and hardware tests. And I will present you some conclusions. So what is forest nursery inventory? Basically, we go around and gather like counting information, size information, how the seedlings are growing, and the health situation of them.
What are the safety glasses for? I saw that sign and I was wondering, why does it say wear your safety glasses? Is it laser or?
Oh, that's the Spanish setting. Yeah, I have no idea. I just found it off internet.
Oh, okay.
Because it's for inventory, he's using like laser scanners.
Yeah, it's probably laser. Yeah, okay.
And automation can be really helpful in inventory and phenotyping processes with reducing manual labor and at the same time increasing efficiency and letting you to do everything large scale and do agriculture with the same approach as we are using in industry. And the two big tools on that are robotics and computer vision. So why should we spend money and do robotics for forest nursery inventory? Well, in US alone, annually there is 1.4 billion tree seedlings being produced and sold, and 82% of that is happening in southern states. So it's very big for the economy of southern states. And now these parts are more obvious to this class, but autonomous navigation is navigation without human intervention. Since I'm going to use GPS in my project, I put this also to explain what's happening with RTK GPS. So in a normal setup, if you have a standard GPS on your robot, in agricultural fields, there could be multi-path error. That's where the GPS signals get reflected from the plants and whatever is around your robot, and then you have lots of errors, so your localization can be not so accurate, and also there are errors induced by weather. So for that matter, we are using a differential GPS setup. We have a station, we have the rover, and there's going to be real-time correction messages between them. And also I have visual navigation. I have used visual navigation for the robot. So there are two experimental scenarios that the robot has to be useful for both of them. Some seedlings have centripivot rows, some of them have straight rows. So for auto steering, I have, or visual navigation, I have developed the following pipeline. So we have Z2 stereo cameras. It gets RGB and depth image, and we use OpenCV on them to find the beds and have the robot follow the beds, even if there is no GPS data and it doesn't have a pre-built map from the field. And all of that is happening in ROS. So this is the GPS waypoint following algorithm that I've used. This is the computer vision. For computer vision or in-row steering, I'm just using a P controller. In simulation, it's working good. Let's see about future more experimental tests. And for the GPS waypoint following, I'm using a PID controller. It uses the current position, the goal position, and the compass on the robot gives us the heading of the robot. So we use a PID to control the heading and go towards the goal position. Now, since we have two navigational algorithms, there is going to be a priority order on them. So whenever vision is available, it's more reliable, and we are going to go with vision. But at the headland turnings, there is no row detectable. That's when GPS data we will use. And if none of them are available, the robot is going to do emergency stop or just a stop. That robotic software or the algorithm was implemented in WebOps environment, and in WebOps I developed a environment to look like a forest nursery and model the robot. And in WebOps we can do programming and see how the robot will operate. This was the visual navigation pictures from the camera, the simulated camera on the robot. You can see the workflow. It does canny edge detection to find the beds and do auto steering. Here is a short video of the end result of the simulation. As you can see on the bottom, camera feed, it detects the row and follows it. Now in the headland turning, it's just using the GPS data. So we don't need to have a pre-built map. As long as we have the coordinates of the headlands, that's good enough for the robot to have its first operation. But during this operation, it's recording all the GPS coordinates of all the points is passing through. So we are making a map. These are the results of the simulation test that I had. As you can see, I used deviation from planned path as my evaluation metrics to see how good the navigation algorithm is. And this is how increasing the speed of the robot affects the accuracy or fitness of the navigation algorithm. Basically, the higher the speed, the less the accuracy.
Do you happen to know for that diagram on the right, do you happen to know what speed that was recorded at?
Probably the least one, because I wanted to look.
Yeah, well, that's what I was wondering, if the overshoot is what makes it increase.
That's the overshoot. There is, I tried whatever I could. I couldn't make it less than this. All of them have overshoots.
Right. Yeah.
But I couldn't.
Yeah.
And the whole simulation helped me have a 0 to 100 steps of the whole workflow, so that I can at least before the full test, I know what's gonna happen everywhere. And then helped me find potential bugs or actual bugs that I had to fix, and also I checked how the speed affects my algorithm. So then we also modeled a robot that you can see on the right, and on the left these are some robots from literature. And we were planning to make the one on the right, but with some few, and this is the schematics of the robot we modeled in SolidWorks. We fabricated it with the help of technicians and research engineers. It didn't come as beautiful as in the picture, but it can work. This is the robot. It has aluminum body, differential drive configuration. It's a development platform, so basically we can add other modules with different functionalities to it, such as beading or spraying, precision spraying. And it has an adjustable configuration, so if you see the body, there is like, instead of these short bars, we can put just longer bars, and everything is with nuts and bolts. So if a nursery has wider beds, narrower beds, there are several different standards in nurseries. We can reconfigure it and make it work with them. This is the system control schematics. We have a data acquisition layer, both the data from seedlings and data from environment. The data from environment is gonna be used to navigate our robot. For navigation layer, we have the processor as well, and the processor is gonna process the environment data and send commands to the drive layer, which are the motors. And other than the robot that I showed you that was built, we also bought an off-the-shelf robot called Amiga, and it's really good for developing robotic platforms, because as soon as you buy it, it's already working. You just try to work on the software part. You spend less time on hardware connections. This is the data collection. We tested it separately, and there's a push where it bends over the seedlings so that we can see their stem better, and do visual processing to measure the stem parameters and also count them. Same setup will be was mounted on the robot that was fabricated in our department. So we are going to do the same process with the robot instead of a tractor. Here it's mounted on a tractor. And using the Z cameras, we can also do spatial mapping and have a map of the field, both a 3D map or just keep the GPS coordinates and do a 2D map. This is the canny edge detection. This is real time happening on the depth feed from the stereo cam. So you can see it here. So from the edges, we know the direction that we should be going towards, and that's how we control the robot. And this is the map that was built from the field using the Z spatial map. All right, now there are some evaluation methods that as I'm working more on my robot and getting it more prepared for more intricate testings, I'm going to be using them to evaluate the navigational algorithm. One of them is how long it can operate without human intervention. The other one is deviation from planned path, adaptability, if there are subtle changes within the environment, is it gonna still work on all smoothness and efficiency. Like if it's supposed to cover a field, can it do it with less battery usage or no? There is success rate and task completion time. And these are some evaluation metrics that I'm trying to use. This was my what I've done up until now. Ongoing work is trying to do remote control of the off-the-shelf robots, georeferencing the data, working more on road transitioning in actual robots, not the simulation one, and performing more experiments. Future work will be including industrial cameras and also using machine learning based approaches for navigation. Thank you.
All right, that's great. That's really nice to see all those outdoor pictures. Anybody have some questions?
Where do you test the robots?
There are lots of nurseries, like down in Alabama, Georgia, and also South Carolina, full of nurseries.
Follow-up question. On your simulation slide, you said it worked at speeds up to 2 meters per second.
Mm-hmm.
What caused it to fail at 2 meters per second?
Oh, it was overshooting. The overshoot was so much that it wasn't covering the GPS waypoints, so it had to go back and then overshoot again.
Okay.
Yeah. Well, of course, if we develop the program more to add conditions to it, like if you missed one, but you're covering the ones in front of it, just don't care and go with the flow, or stuff like that. But with that software I had at 2 meters, it was just getting out of control.
Okay.
Are you running the canny edge detection on the depth image?
Mm-hmm.
Okay.
Because it's already grayscale, perfect.
Do you think that overshoots just something you can tune out of the PID controller, or have you messed around with tuning that at all?
Yeah, I did. There is I found a paper like with some rule of thumbs about how to tune PID for mobile robots. So it would say, for example, first let it wiggle, then divide the P by half, something like that. I tested that. Also, I put random numbers, but yeah, maybe we can have a like experimental, like design of experiments, 20 experiments to see if it can be further fine-tuned.
How would you, in real life, how would you keep the camera lenses clean as you're moving through a field? I imagine there's a lot of dust and debris being thrown around.
So, as you can see here, the cameras are on top of the seedlings, but the tires are away, and also the bed is raised. So usually there is not much dust, not that much dust near the cameras. Now we use here. I'm not sure if you can see it, but for GoPros that we use, we put the shield, the dust-proof shield.
Okay,
So,
yeah.
Even if it gets dusty,
Still works, huh?
yeah,
Yeah.
stuff can be applied in the post-processing of the visual data, because we don't need, right now, we don't need the data on seedling real time.
Uh-huh.
It's going to be processed after the data collection. So,
Well, it's interesting that humans and most animals have built-in windshield wipers, right? We blink our eyes and clear and so it just, I thought for a long time, all these cameras that we use outdoors should have some sort of little windshield wiper or something that
right.
keep them clean for best results, but, you know. Well, that's great. Thank you very much. I appreciate Appreciate it.